The lab of Kepler's law. So before I get to the lab, let me show you the theoretical explanation of the let's say this is Newton's version of Kepler's third law. So this is it relates the orbital period and distances and masses of any pair of orbiting objects such as sun and a planet, or in this case Jupiter and the moons. So this little m is mass of the moon and big M is mass of the Jupiter, and the relationship T, which is the orbital period, that means how long it takes for the moon to go around the Jupiter for one complete revolution. That is T squared should be equals to 4 pi squared over G. G is universal gravitational constant, the value of which is 6.67 times 10 to the negative 11. And this is the mass of the Jupiter, and this is the mass of the moon. And this is the radius of the orbit, which is the center of the moon to the center of the Jupiter, the distance. So the idea here is because the mass of the moon is so small when you compare with the mass of the Jupiter, so you can safely ignore this, and T squared would be approximately equal to 4 pi squared over G times the mass of the Jupiter times r raised to the third. So when you solve for the mass of the Jupiter, and it should be equals to 4 pi squared over G times r cube over T squared. So this number is very important here. If you know this number, multiply this constant and you got the mass of the Jupiter. That's the idea. Let me get to the lab. When you get to the lab, so you will see the 4 moons of the Jupiter are moving around. So this is the face-on view. Actually they are going around, but you will see just they are going back and forth. So the first moon, which is closest to Jupiter, is the moon 1, and then the next one should be moon 2, and so on. The most important thing first here to look at is the field of view is 300 arc seconds. That means there are 10 grids, and then total 10 grids should be equals to 300 arc second. So one grid would be 30 arc second. If it is a half of the grid, it would be 15 arc second. So let's say your moon was over here. The maximum distance of the moon, let's say, can pass is, let me track this moon. So the maximum it can go is here, and it's going to go back. So from this distance to the point, it can go all the way here. So you have to track down how many grids it can pass by. So that many grids times 30 gives you the angular width of the orbit in arc seconds. So that number goes here. Then you got to convert that angular width to the diameter. So the planet is this distance from you. So this distance times the angle in radian should give you the diameter. So how do you get that? So first you got to convert that into the radians. So first, whatever the arc second you have, divide by 3600 will get you to degrees. And once you have the degrees and you multiply pi over 180, then you have the angle in radian. That radian angle times this distance can give you the diameter of the orbit in meters. So once you have the diameter, you can just divide by 2 to get to the radius. And then for the period, you need to track down here. So let's say the moon is over here, and wait till moon moves. Let's say this is over here, and it's gonna go and wait all the way when it come back, and then the difference of the time is the time period. So that time period should be in seconds, and then you can put one over here, and then you can calculate the rest of the quantities. So I hope this can help you a little bit. If not, please call me during the office hour, and then I can help you.